Started. The last speaker this morning ran late and shortened our lunch hour. It was a travesty, but that was me. So well, I can't do that again. Okay, thanks those of you who have returned. I'm now going to continue this journey into exploring generalizations of linear function learning, but I'm going to switch to the next major topic area. And the switch is dramatic. I'm going to shift focus entirely from the input space and even regularization on the model to entirely looking at what's happening at the output space. Okay. Interestingly, and most importantly, if I forget to emphasize it, although I probably won't, is that whatever we've done so far all stays in place. Everything I'm going to show you now, which is focused on output space modeling, is completely orthogonal to everything we've done. What does that mean? That means nothing I do will impact anything we've done already. So whatever feature expansion, local feature expansion, kernel, regularization, training technique you like or dislike about what we've seen so far, none of that is impacted by what I'm going to show you now. Okay? And in fact, this is empowering because people often get confused about, what's the source of kernels and what are the interactions between what's happening on the input side and the output side. And in fact, there's very little interaction. Okay? And so it's important to keep these things separate. If you look at the output side of the equation, so far all we've been doing is learning linear models, yes, but even silly linear models. We've been learning how to predict a single scalar output. Okay? Predicting scalar outputs, though exciting, is not a particularly widely applicable problem, and it would be really interesting to do two things. One is to extend the output from scalar to multivariate, and then from multivariate to structure. But the other thing that we need to do is to change or generalize the model, the output side of the model, from just a linear output to a nonlinear output. Okay, so those are the two major topics that I have left to cover in terms of generalizing the models before I start talking about latent variables. So I'm going to do those two things, at least start one of them and finish one of them today. What I'm going to do first, though, is stay with scalars and hope I can maintain your attention a little bit, but introduce this idea of a nonlinearity at the output level. And discover that even though naively this looks like it gets us in trouble, there are actually very elegant, very general, very powerful things we can do here. Okay, so now looking at output representations. So topic 1, output transformation. So we'll still be looking at scalars for just a while longer. So how do we motivate this? Well, so say we're still doing scalar predictions, so we have some scalar variable y we're trying to predict given some input. But what if y is special? What if it's not just some arbitrary number on the line? What do I mean? What if there are things going on in y, like maybe we know for some reason y is a non-negative number. Maybe we're predicting heights of people. It's hard to have a negative height, right? Or weights or something, okay? So it could be the case that the range, the space into which we're predicting, has some natural structure or some natural constraints, say like non-negativity. Another natural constraint at the output side could be, perhaps it's a probability. Whatever it is we're learning to predict, it's some number, but it's guaranteed to be between 0 and 1, right? If you want to train an output predictor like that, really, do you think you should be minimizing squared prediction error? Do you think you really should be learning a linear model? Okay. Another type of structure we'll encounter on the output space, at least in the scalar setting, is a class indicator. Maybe we're really interested in a classification problem, say a binary classification problem, where we have positive instances and negative instances. Okay? Each of these things are constraints on the output space. All right? Now, the problem is, if we don't do anything, and we just tackle this problem with linear predictors, we have a range problem, which is the range of a linear predictor. It maps all of R to all of R. Okay? So just, this is dumb, but think it through. What if I have to constrain, what if I know all my data, all my target labels or target scalars are probabilities, numbers between 0 and 1. And I'm trying to learn a linear model over, say, an input space, say an unbounded input space. What linear models guarantee that your predictions stay within that same interval? there's a whole infinite family. It's a very rich, interesting family. That family is the constant functions, right? If we do anything other than constant fitting, what we'll lose is the ability to guarantee that our outputs stay within the legal interval, so we'll start predicting probabilities that are -5 and +12, right? Excuse me. And you could imagine that your client or in the application area may not be so impressed with your probability predictor that's saying, you have a minus 95% chance of rain tomorrow, right? So we would be able, or we would like to be able to impose natural constraints on the output side and have those constraints respected by the predictor, okay? Now there's a cheap and dirty way out of this, which is to say, no, we like linear models, we don't want to lose anything we've accomplished, but that would be silly, but say you're like that. You could add constraints on the training data. So I give you a finite training sample. I could certainly enforce a constraint that on the training data, your predictions are constrained to be in some range, okay? Well, fine. Well, we're going to struggle a bit with this discrete class indicator constraint, but even in probabilities or non-negatives, even if you impose that constraint on the training data, of course, there's test data, and enforcing the constraint on the training data does not guarantee it's enforced on test data. And again, we have this problem that any linear function is unbounded except the constants, right? So there's no way to guarantee on all test data that you would respect the constraint unless you start imposing artificial restrictions like, let us declare that no test vector has a magnitude beyond some bound, yada, yada, yada. Okay, it's going nowhere, all right? Well, it turns out, though, that there's just a simple, elegant, perhaps right way to do this that just obviates all of these issues, okay? All we have to do is just generalize our model with one simple step, okay? And that one simple step is forget about linear, right? What we need are nonlinear predictors, okay? And what we're going to do is introduce, I'll call it cleverly a function f, some nonlinear function, right, that we will impose as a transfer, okay, over your linear predictions. So what we're going to be doing is still trying to learn a linear map, but then the output of that linear map is put through some nonlinear function, okay? And I'll say a lot more about that shortly. So this is sort of the picture. It's no longer the case that your linear response, so you have some weight vector and you have some input feature representation, you take an inner product, you get a number. That number is not your prediction anymore, okay? That number is what I'm going to call your pre-prediction. That's the linear response you get before the nonlinear transform. But you're going to take that pre-prediction response, you're going to put it through some nonlinearity, and then you're going to get a post-prediction response. And that post-prediction response, let's call that y hat, is your prediction, okay? And we're going to choose our transfer function here, or this nonlinear transfer, to ensure that the range of the function respects, say, for example, some range constraint that we have on the natural data, okay? This is most easily seen with examples. So, for example, say we're really interested in non-negative data, and we would really like it if our predictions were non-negative always. Just because that's the way the world is, okay? Well, here's a pretty obvious transfer we could use in that case. What we could do is just learn our linear model, get our linear response. I'll start calling the pre-prediction values z hat instead of y, okay? Exponentiate, and then we'll get some post-prediction value y hat, okay? And quite clearly, the exponential function maps all of r into r plus, okay? So if we impose this kind of transfer function, the range of the transfer function automatically satisfies the constraint, and we never have to worry about it, all right? Similarly, if we're trying to predict values that happen to be probabilities, numbers between 0 and 1, well, same idea. We just choose a suitable transfer function whose range respects the constraint. So here, a natural choice would be what's known as the sigmoid transfer function, 1 over 1 plus e to the minus z hat. Which has this shape here, right? It's sort of like the 0, 1, tan h. So we take any pre-prediction value, we put it through there, we get a probability. So the sigmoid maps all of r into 0, 1. Actually, into the open 0, 1, but okay. So, if we're interested in probabilities, maybe we're going to be interested in using transfer functions like sigmoid. Okay, what if we're really interested in classification? That is, the only y values you will ever see in this application area are +1 and -1. That's it. Nothing in between, nothing outside. okay? Well, sure, we could easily come up with a function, say sine of z, which maps all of r into +1 or -1. Okay, and then you make some decision about what you're mapping into at 0. Okay? Anyway, same idea, right? So we impose some function between the output response of the linear part of the model and the final prediction in the space. And here we can see already a few things going on, like you could have a smooth, differentiable transfer, or you could even have discontinuous transfers. You might guess that computationally there are going to be huge consequences based on these choices. Okay. But the idea is simple. Seems like a reasonable approach. The question is it a good idea? And if you don't think about it too carefully, you might actually convince yourself that it's not a good idea. It's not going to work. It's not going to work for a very simple reason. That if we forge ahead, we'll get into trouble. So here's the worry that you have, right? Well, sure, I impose some fancy nonlinearity, and then I'm going to fix some loss function. So here's a little demo. Say I'm going to fix my prediction error to be least squares, but I want to predict probabilities. So least squared prediction of probability values. It already should sound like a bad idea, but anyway, okay. We go ahead, and then we impose our happy sigmoid transfer that maps into the probability range, okay? And then we get our training objective. And then we have to minimize this function, the sum of the squared errors between our output predictions and the targets with respect to our linear model parameters. And we immediately discover that we're hosed, right? Like we're cornered here because what we're going to get are definitely non-convex optimization problems. Okay? Actually, this case is particularly easy to understand, and what's remarkable, and I'm not trying to diss anyone, okay, but if we were in this room 20 years ago, we'd all be going, yep, well, that's the way it is, we just forge ahead, okay? And I'm going to tell you that that's daft, right? We know what to do in this situation, and I'm getting to that shortly, but honestly, we, at least older we's, didn't know what to do in this situation 20 years ago, and it was a big advance, a huge advance, to get over this little barrier that we're going to see right now, okay? Nevertheless, if you just forge ahead naively, we are definitely going to get non-convexity. Why are we going to get non-convexity in this case? Well, think of a single training example. You have a target, some y value, and y is maybe in the unit interval, okay? And then we're trying to tune this weight vector, but no matter what we do to the weight vector, we just get this inner product on that same example, so we get a scalar response on that one training example, and by moving the weights around, all we're doing is we're shifting that scalar response, okay? But that's the pre-prediction response, so we're moving that scalar response around on the real line. So let's think of that as moving here, this being the axis where we're moving the z hat value on a particular example, okay? So we're moving z hat on a particular example, but there's a fixed y. So there's going to be some magical z hat value that gets 0 prediction error, okay? But what happens is if we move z hat with a sigmoid transfer to plus infinity? Well, it doesn't go to infinity, it goes to 1, right? What happens if we move z hat to minus infinity? Well, the y hat, the transfer of that, goes to 0, okay? So what's going to happen is we don't get like a quadratic surface that we're optimizing in. What we're going to get is something that saturates. It flattens out, right? So the sigmoid is going to flatten out that quadratic. And flatten out that quadratic, and we get a bump. Okay, well, one little bump. It still looks, it's quasi-convex. It looks like there's a unique global minimum. We're okay, but that's one training example, right? If you take multiple training examples, what you essentially do is compose these bumps, and you get things like this. Okay, and we did it to ourselves. We've created this kind of training problem, and look, we're in a world of trouble. Okay, smart, hardworking people, and me and others, 20 years ago, were saying, "Wow, gee, I guess you can't have nonlinear transfers then." Okay, and people were doing the following: they were running experiments, saying, "Okay, we want to predict probabilities." And we fixed the sigmoid transfer because these were called neural nets, and you just use sigmoid transfers, okay? But what we were doing, people were doing, we were investigating different losses for training your neural network with a sigmoid output transfer to predict probabilities. And they would try least squares, try absolute error, try cross entropy error, try all kinds of stuff, and then run a bunch of experiments and find that some of these don't work very well, some of these work really well. And one of the conclusions people were coming about just naively and empirically is actually, squared error seems like a bad idea for probabilities. You should use something more information theoretic, like, say, cross entropy. And in fact, if you run the experiments, it just seemed to work a lot better. Okay? What they didn't realize initially, but became obvious in retrospect, is the difference between using a quadratic loss and, say, a cross entropy. We'll see more about it shortly. The difference is dramatic. The difference is an optimization problem that looks like this, or a convex optimization problem. So in fact, what they were comparing wasn't really the quality of error assessments. What they were comparing is global training versus local training. They were comparing an algorithm that could train to get the global solution and then regularize versus an algorithm that had to actually pick some arbitrary local minima out of a space like this. And it won't shock you to discover that being able to train the model is actually quite helpful. Okay? But this was not understood, and now we understand exactly the connection between choosing the transfer and the loss function that should go with it. And these things are coupled. This is not an arbitrary choice. You don't just pick sigmoid and least squares. Well, you could, but good luck to you. Okay? So what was sort of, sorry, just to hammer it home, there's this pretty famous paper, actually, in NIPS, that showed you could make this arbitrarily bad. So the combination of sigmoid and least squares could easily lead to an exponential number of local minima, exponential in the dimension. You could just basically line up these bumps in the different dimensions, and you get these interference patterns, and then now you're trying to train your model in a crazy surface like this. It's really hopeless, okay? Unless you like global optimization is a fantastic field. It's very wonderful and interesting, but people never come back. Okay. So anyway, maybe we should be trying to avoid that. So this is the idea, and actually it was an idea invented by one of the speakers in the summer school, Manfred, who will be here shortly. But it's a beautiful, elegant idea that ties into an older, beautiful, elegant idea developed in Russia in the 60s, like everything else, okay? But here's the idea. Let us not just randomly and haphazardly pick an arbitrary transfer and an arbitrary loss. Let's think, right? If I pick a transfer function, I needed to pick a transfer function, right? I have to map into a certain range because the data demands it, okay? So say I've made that choice. Can I actually understand how a loss function should be associated with that choice so the training is still tractable, okay? And it's actually really easy, and everything you need to see is in this picture, okay? So here's the first setup of what's called a matching loss, a loss that's matched to the transfer function, okay? We're going to take our nonlinear transfer. We assume we've already fixed it, okay? However, it turns out the examples I showed you, did satisfy some properties, and we're going to need this transfer function to not quite be arbitrary. It has to satisfy properties. In particular, we're going to need it to be continuous, so no sine function, okay? But if we pick a continuous, differentiable, nice smooth function, and strictly increasing, okay? Now think this through, right? We have a pre-prediction linear response and we're mapping to an output space. You really don't want a non-monotonic transfer because it's sort of like, I get bigger and then my prediction gets smaller and bigger and smaller as I just monotonically get bigger. That's crazy, right? Just pick a function that's monotonic, okay? So a smooth, differentiable, monotonic. In fact, let's make it strictly increasing, right? No flat spots, okay? If you do those things, then there is a specific construction you can use to recover a loss function that guarantees your training problem is convex and you can train it, okay? And it's just a trivial exercise in calculus. Maybe the picture's more helpful. But what we're going to do is we're going to define a loss function now, L, in terms of a little f, okay? And here's sort of the geometric picture. Here's just a definition. You say the loss between a pre-prediction value z hat and a one further thing I should point out. So I have pre-prediction, post-predictions, okay? So I have a pre-prediction z hat and then a post-prediction f of z hat. Okay, that's me, in my model training side. But of course, the data has a target value y. Well, that y also has a pre-image, right? So we have a pre-prediction target and a post-prediction target. We have a pre-prediction, linear hypothesis and a post-prediction linear hypothesis. So there's these four objects: y hat y, z hat z. Okay? So here I'm defining a loss. I basically am defining a loss between y hat and y, or f of the pre-predictions. Okay? So I'm defining a loss between y hat and y in terms of these pre-prediction values. And the way I'm going to define the loss is an integral from the pre-target to the pre-guess of this difference integrated. And it just corresponds to this picture. So we have the pre-predictions here, we have our nonlinear transfer, and then we have the corresponding post-prediction values. And we're going to try, the loss is trying to measure how far apart should we say those two values are. You know, are they close? Are they far? And the way we're going to measure that distance is by this little integral, this little area. So the distance between as we integrate between the pre-prediction values of the difference of the transfer. Blah, whatever. You can look at it a bit later. It's just that picture, okay? Well, anyway, we take this picture. It's an integral, and then we solve this. Well, we solve this. To solve it, what we're going to need is the antiderivative. Of course, this is like first-year calculus. I'm sorry. But anyway, you need the antiderivative of the little f, which is a big F. You know, big F is a function such that big F prime is little f. We've seen this before. Okay. And so we solve it here, and then we get this form here. Okay, so this looks like a mess. It is not. It's beautiful. It's powerful. In fact, this thing we got just by accident is a Bregman divergence. I haven't defined it for you yet. Maybe some of the other speakers have, but you're going to be seeing it for sure lots through the rest of this course. Okay. Anyway, I won't dwell on the definition right now, but we get this form here, which my claim is a beautiful form. Okay, and it's much more familiar to you than you might expect. Okay, a few facts about this definition. So this, my claim is that that form is a loss function, and it's a loss function that has many nice properties. So let me just tell you the nice properties that that definition just automatically created for us. So we picked a transfer little f, we construct a big F from little f, the antiderivative, and then we construct a loss from big F and little f. Okay? What properties does that loss function satisfy? Well, okay, first, what properties does big F satisfy? The first thing we know about that big F function, the antiderivative, is it's guaranteed to be strictly convex. Why is it strictly convex? Well, look at its second derivative, right? Well, the second derivative of big F is the derivative of little f, but we said little f had to be strictly increasing, which means its derivative is strictly positive. Strictly positive. Okay, therefore, f double prime of big F double prime is strictly positive, hence it's strictly convex. So what? Okay, well, if it's strictly convex, well, now we're just looking at a function f, and we can just go back to basic properties of convex functions, in particular, first-order Taylor approximation. So take your big function f and look at its first-order Taylor approximation. That would be this picture here, expanded about z. Okay, and this is the first-order Taylor approximation expanded about a point z. Okay, and what do we know about convex functions? We know that the linear function here, so z is the constant, z hat is the variable, right? So this function of z hat, this is a linear function, that's a nonlinear function, okay? And we know that the linear function is a supporting hyperplane, right? Strictly below. So we have a strict inequality. So what? What's the big deal about that strict inequality? Well, the definition we had, this thing we got at the bottom, that is the difference between the convex function and its first-order Taylor approximation. And therefore, this is guaranteed to be non-negative because the function is guaranteed to be above, right, the linear support, right? So strictly non-negative. So like a loss, right? It's even better than that. Because it's strictly convex, it turns out that the only point, there's only one point where the difference between these two functions is 0, and that's at this point, and that's basically the zero loss point. Okay, so anyway, you know, through this little calculus construction, we've constructed a loss function from little f that's guaranteed to be like a loss function. It's non-negative, and it's 0 only if your pre-prediction values exactly agree. Your guess to the target, or even in terms of the post-predictions. Looks like a really nice loss. It's even better than that because by construction, if we look at the training problem here, the training problem is the z hat, right? The z hat is the linear response. So we have some linear parameters we're tuning. We're getting different z hats. This is guaranteed convex in z hat. Trivial observation because the only place z hat appears is in the convex term here and then linearly there. And you know, convex plus linear is convex. So we've constructed a loss function associated with the transfer, guaranteed to be a loss, guaranteed to be convex. Okay, that seems nice, right? That should be a good NIPS paper, okay? Actually, that was a fantastic NIPS paper because it both had the exponential minima problem and this solution. That's like 2 great NIPS papers. Okay. Now, it's not just an arbitrary construction. It turns out that this construction kind of for free recapitulates all this history of like designing loss functions in various settings. So this story I alluded to about neural net researchers 20 years ago, trying to figure out what loss function they should use to predict probabilities. Well, it turns out the cross entropy is associated with the sigmoid. It is the matching loss function for the sigmoid. They just didn't have this concept at the time. Okay, and so this definition, if we pick natural transfers, actually inevitably recovers natural loss functions that people will invent by independent means. Just a quick demo. If I pick an identity transfer, so we do nothing, just linear prediction, but then we go through the trouble of figuring out what's the potential function. It's a quadratic, convex quadratic, and then we plug in all the definitions. We discovered we've reinvented squared prediction error. Okay, so this is sort of like saying if you want to predict, if you just want linear predictors with no transfers, okay, least squares. Okay, and I don't know, I've been dissing least squares already, but least squares is a matching loss. Okay, if we pick an exponential transfer, well then we do get a natural loss function here. It's called the unnormalized entropy error. It has some other names in information theory. I've forgotten them off the top of my head. But anyway, this is a fairly famous loss function also. Okay, and then finally, the one the neural net people would have really benefited from 20 years ago is if they pick their favorite sigmoid transfer and then just go through this construction, out pops cross entropy, KL divergence. The KL divergence between the probability distribution that's the target here and your guess. Okay. All right, you don't look impressed, but anyway, this looked really neat to me. Okay. So the conclusion is, if you have some output domain, still scalar, okay, but you have output data and it's got structure, it's got some kind of constraint, and you'd like to respect that constraint, and you want to still stick with tractable training processes and all of the linear modeling apparatus we've seen up to now, there's no problem at all, right? You just pick whatever transfer you need, as long as it's differentiable, increasing, yada yada. Look, you just look up the transfer and the loss you need, plug it in, and you just get a tractable training problem, right? You get a convex loss minimization, and you learn your linear weights over your features, okay? But your predictor is still nonlinear, right? So both in training and in test, you don't just take your linear response and use that as the prediction. You take your linear response and you map it through the transfer into the domain. This is so easy. In fact, this should be like lecture 1 or 2 of any machine learning course, right? I think I'm on lecture 2 or 3. Okay, so no problem at all. So linear modeling, learning linear functions from data, yes, seems really limiting. But now what have we seen? You can expand out the input space in many ways. You can still control overfitting issues, sort of. Okay, but now we can also impose nonlinearities on the output side. So you can just basically sandwich your linear model between 2 complicated or interesting looking nonlinearities, and you won't be surprised to learn that that's empowering, right? You can now go out there and solve a whole range of very interesting, sort of natural problems that arise, okay? And this doesn't interfere with anything that I've done this morning. They're orthogonal, right? Actually, I should say everything I did up to now had nothing to do with the loss, right? All the feature expansion, kernels, non-kernel, whatever, nothing to do with the loss. Actually, I should be a little more precise. It had a little bit to do with the loss, but only a little. The only way the loss function affects anything on the input representation side that I've told you is the weights, the linear part of the model, the weights have to participate in the loss only through the data, only through the features. Right? So there has to be this inner product of the weights with the features. If that's the only way it participates in the loss, then the loss is irrelevant to all the other modeling. Okay. So what I've just shown you also maintains that kind of property, so it doesn't interfere at all with what we've done. Okay, so next step. So you may think that's kind of not so cool, But the reason you're thinking it's not so cool primarily isn't linearity so much anymore, because I think you're starting to see how linearity is giving us very powerful representational and computational tools, okay? The reason this is still uncool is, like, you know, come on, scalar predictions, right? We're taking, what am I gonna do? I'm gonna take a video and produce a number. Like, yeah, okay, there's some utility in that kind of capability, but you know, a lot of the motivating applications we'd really like to pursue are things like the output is also a structure. You know, I want to take a video and I want to understand it. I want to like recognize events and parse scenes and, you know, I don't know, understand sentences, right? I don't want to just say that sentence good, right? You know, we need to now scale things up dramatically on the output side. Okay? Now, it's going to take a couple of baby steps. So the next step is just to go from scalar to vector. Okay? Still finite dimensional output vector. That will be generalizable, but you know, one step at a time. Oh, and that will be the next step. I have an aside. What time is it? That may come tomorrow. Let me think. Okay, there is one further topic still in the scalar realm. Geez, I pitched the vector case, but I'm going to do one more thing in scalars. I apologize, okay? Yeah, sorry, I forgot. I always forget about this issue. But other people don't forget about it, so I need to tell you about it, okay? Still back to scalars. The thing I kind of swept under the rug was classification, right? This hard, like, you know, say binary class problem, +1, -1 labels. You know, frankly, most people look at the probabilistic map like a sigmoid and say, oh, that's good enough, right? Like, you know, I can say 90% +1. That seems great, okay? But, you know, there's still people out there who say, no, +1, -1. Do that, okay? And in fact, you've all learned it already because that's what support vector machines do. And nothing I've told you so far really talk about support vector machines in any way. Kernels have nothing to do with SVMs. I don't know where people got this coupling from. Anyway, okay. Let me just sort of tell you how SVM and related training problems are connected to what I've done, okay? So here's the kind of the problem, is that the one transfer function that we started with that I left out was the sine function, right? It's this discrete -1 +1 step. Very bad function. It has none of the properties we need. It is not strictly increasing. It's not continuous. It's not differentiable. It satisfies not one single thing we need. You cannot hope to do anything like a matching loss with this kind of a function. Believe me, me and others have tried, okay? It just isn't going to work out. But there are reasonable ways you can think about training predictors with this discrete threshold jump, okay? But it's really a relaxation. So let me just kind of pitch to you quickly maybe reasonable ways of relaxing step functions, or at least loss functions associated with steps. Associated with the step function, there is a natural loss function, by the way. It's not a matching loss function, but it's natural. And the natural loss, really, that we associate with the step is the simple misclassification error, right? There's only +1s and -1s, and all targets are +or-1, all guesses are +or-1. There's only 4 things that can happen, and only 2 loss values, right? You're right or you're wrong. Or you could build a little contingency, like cost table, okay? So let's simplify it and think of like just misclassification error. So 0 means no loss, you're exactly right, and 1 means loss 1. So that's the natural loss function for this step transfer. Both of these are very problematic, right? They don't have any nice sort of computational properties associated with them. Okay, maybe quickly. If you want to do a step threshold, like literally just +1 to -1 threshold, we usually draw different pictures. So usually we draw this picture of a line and say that's a linear function. Now the picture is this step, and we change our perspective when we start looking from above, right? So this is the picture you typically see when we're thinking about a sine thresholded or linear discriminant model, okay? But just to get the geometry straight, you know, we have the same old weight vector as before. That actually defines a hyperplane, right? The weight vector gives the orientation of the hyperplane. The length of the weight vector gives the slope of that hyperplane. So there's definitely a hyperplane coming out at you through the screen, okay? But then it's being cut off at 0, right? And this is the cut line, or the orthogonal cut, where the all data on this line has inner product 0 with that weight vector. And then so all inner products are positive on one side, all inner products are negative on the other side. When we apply the sign transfer, it partitions space into a partition of two half spaces, the plus and the minus. Sometimes people get hung up on offsets. The offset would just shift the hyperplane up or down, by some parameter. Actually, offsets could always be just swished away by adding a constant one feature, and then the weight associated with that feature is an offset. The reason people are a bit dogmatic about separating the offset is that if you regularize the weights, maybe you don't want to regularize the offset. Whatever. Okay. You've seen these pictures before. So, okay. Can we recover any of the computational advantages, like we recovered before? For example, tractable training, in the case where we restrict ourselves to a hard threshold predictor and misclassification error. And most of you know the answer. There was a question?
So is offset the same as margin? What is margin?
Coming. Okay, so we have the obvious computational question, which is I give you data, I give you a weight vector, we have to optimize the weight vector to minimize misclassification error, or we could think of it in the previous picture, we just have to find the linear hyperplane that minimizes the number of misclassifications. And then we ask ourselves, is this problem easy or hard? And many of you would know this, but maybe not everyone, so I might as well just tell you, or get you to tell me. The answer is it depends, right? Sometimes this is a tractable problem. You can actually solve this problem, right, efficiently. So forget about matching loss. If you really want misclassification, you can train tractably to get an optimal linear classifier to separate the data, okay? Sometimes it's really happy news. Sometimes, unfortunately, it's really bad news. And when is it happy news versus bad news? When one simple condition applies. Well, there could be variance, but anyway. The main condition is if the data is linearly separable, right? So if your plus class and minus class really are separated by a hyperplane, you can find it. You can find it efficiently. There's many ways to find it efficiently, many incremental online ways, many sort of linear programming-based methods. Let me just give you a particular example. Here's a linear program that is guaranteed to solve for a weight vector and offset that separates the data if the data is separable. Okay? And it even gives you a certificate. So these little auxiliary variables are going to be like sort of the, what I did in the first lecture, these little like local cost penalties, one for each example, right? And these will be a certificate. If they're all 0, then it's a proof that you have separable data. And if one of them is non-zero, that's a misclassified example. And it's a proof, because the linear program solves this, it's actually a certificate that it's not linearly separable, okay? That linear program is polytime. Okay? So, you can tractably determine whether or not the data is linearly separable, and if it is separable, you've found a separator. That's easy, okay? What's not easy is if the data is not linearly separable, then, well, you would like to find, what would you like? How about the minimum misclassification error linear separator? Well, of course, it's not unique. There's always some wiggle room, but pick any minimum misclassification error linear separator, and that's famously intractable, right? Which I've already alluded to before. It's NP hard to compute a weight vector that minimizes the misclassification error in general. It's NP hard even to approximate. It's actually really bad, okay? And there's all kinds of, well, anyway, there's all kinds of heuristic algorithms and so on. But this is kind of what we expected. So it's good news that if you can really separate the data, you can just solve, okay? But in a case where, maybe even because of regularization or sort of model selection issues, you can't exactly fit the data. In fact, you don't always want to exactly fit data, right? This is problematic, okay? Like we probably should have saw coming. So here's sort of the question, what do you do about this? And there's two generic responses. One generic response puts us back to matching losses and say, come on, don't use a function like that. Use a nice smooth one, and then all your troubles go away, okay? So we're fine. But the other response is actually to persist and say, nope, we want hard classifiers and we got to train them, okay? The exact training problem is intractable. So let's find another way around, okay? And the other way around is to, for training only, replace the target loss with a fake loss, right? Train under a fake loss and then test under the real loss. and hope to God there's some relationship between the fake loss and the real loss that gets you out of trouble later on, okay? Well, that sounds silly, but okay, there are many paths to any idea, but this path leads you to things like support vector machines. Now, I have liked support vector machines, okay, but it's, you know, I don't know, is that really such, okay, well, you judge, okay? But let me just show you how we get to things like support vector machines. Oh yeah, so here's the idea, right? We're going to persist and we're just going to use a fake loss for training to make our training problem easy. Instead of writing papers with the word fake loss in the title, you come up with a word like surrogate loss, okay? So you pick a surrogate loss, you train on that, and then you swap it out when you're doing test. Okay, now how do you pick, so it turns out though you should use some judgment in picking a fake loss, okay? For example, we want to do +1, -1 classification, and then we get to pick whatever loss we like. So we could say, oh, least squares. Actually, this is a very popular choice in the 60s and 70s. You know, even though classification, just do least squares, right? Well, it's fast, but it seems crazy. Why does training under least squares or even least absolute prediction error seem crazy? Why do the regression losses seem really silly in the classification context? Well, one intuition is, you know, they're going to do things like penalize predictions that are like too correct. So what do I mean? You have some target value +1, and then you're training your model is just moving a pre-prediction value around, right? If the pre-prediction value is above 0, you're thinking that's great, right? Because later on, when you measure test error, that's 0 error. Okay? But least squares is going to say, well, look, the target was +1 and you predicted +10, that's bad. Well, that's silly, right? So, you know, regression losses usually just don't make much sense here. So the whole idea behind surrogate losses for classification is to pick, you know, fake losses for classification that are at least better related to the misclassification error that we really care about later, okay? Okay, so among surrogate losses, the family of losses that have, at least in some circles, become called margin losses are really fake losses that are designed to allow tractable training in a misclassification error setting, okay? So what do we mean by margin loss? Well, it's a loss that's a function of the margin. Okay, so what's the margin? Well, it's actually a very simple idea. Remember, in this setting, we're assuming that the scalar target is a ± 1 value. Okay, so we've got some target ± 1 value, and our linear model is learning some pre-prediction, which is any number, you know, any real number. Okay, the prediction margin is defined to just be the product of those two numbers, which doesn't do anything fancy. It just says, well, look, if you wanted a positive target and your z hat is positive, and you multiply them, that's positive. So positive margin, good. Okay, if the target was negative and your guess is negative, that's also good. Right? And it gives you a positive margin. So margin is just a product of your pre-prediction guess and the target, and positive good, negative bad. Right? Under misclassification error, negative would be misclassification error 1, positive would be misclassification error 0. So we'll start seeing the obligatory diagram shortly. Okay, what's a margin loss? A margin loss is some loss that only depends on your model through the margin quantity. So it's just a function of the margin. Okay? And I'm not selling this. I didn't even make it up. I'm just telling you what it is. Okay? It's probably easiest just to understand by a few famous examples. So margin losses have actually been reinvented independently in different pathways, but they settle on things like the following. So here's a famous margin loss. It's called the exponential, right? And it's e to the minus margin. And it gives you this negative, or this swapped exponential. And I guess it's too faint, but under here is the 0,1 misclassification error. Okay? And we can see this happy exponential living above that misclassification error. It's got wonderful properties, like the exponential is an upper bound on the misclassification error. Isn't that grand, right? So, well, I'll come back to that later. The exponential is convex. Right? It's a convex function of z hat, hence the model parameter, so you can train under that loss. Okay? And if you're doing that, you would be doing what used to be called boosting. Well, it's still called boosting, but I think we're using boosting to mean too many things. Okay, it's a loss that people come up with. Now remember, this choice of margin loss is meant to approximate 0-1 misclassification error, right? So you're supposed to look at this diagram. Here's your target loss. Here's your surrogate, and you're supposed to be really impressed with the quality of the surrogate to approximate that target. Isn't that an impressive approximation of the step function? Okay. Well, maybe not. If you came from a different field, say statistics or somewhat, here is another cost function of the margin, the binomial deviance, but we would just call it log of 1 plus e to the minus margin. And you plot that function, and it looks like that. And then you say, well, that's another very impressive approximation of the step function. Well, it is convex. Actually, it turns out this is quite a bit more effective. So the one thing that the exponential is hiding, but you quickly discover, to your horror, is that it overfits wildly. That is, it grows exponentially, which means if you have an outlier, like one little pesky example way off in somewhere, and it's mislabeled, that's the one thing you're going to be focused on, right? Because the exponential is going to go, wow! That's a big error. The binomial deviance, you can't quite see it, but has a wonderful property, which is it becomes actually linear in the limit. So it's much more robust, right? If you have these outliers, the binomial deviance is going to be much less attracted, although unfortunately still quite a bit more attracted than misclassification. But anyway, much less attracted to outliers than exponential. Okay? So you're kind of getting the game of like margin losses, like what you want. Okay, here's what you want in a margin loss. You want the tightest approximation of that step you can get while still being convex. What a nasty game to be stuck playing, right? Binomial deviance expressed this way, you might note, has lost the upper bound property. You can fiddle around and get it back, okay? Okay, finally, we get to support vector machines. The support vector machine, well, this is a different way of arriving at it, okay? But we could say, well, how about this? I think about what's the tightest convex approximation to a step I could come up with, and all I can come up with is this fixed slope and then a threshold, right? So just zip, zip, and that looks like a hinge. Let's call this the hinge loss, okay? So we have the hinge loss, which is an upper bound on the misclassification error. And it almost feels like, that's like the tightest convex upper bound on a step function you could get, if that even makes sense, okay? It has the same property. It definitely chases outliers, but at least only in a linearly growing way. Now, people have definitely started to say, chasing outliers is bad, and have formulated things like robust losses, like say a negative tan h. But we can see here we lose convexity, and if we lose convexity here, we lose convexity in our training problem, and that's bad, at least from a perspective of training, okay? In fact, if we're going to start playing this game, then why not just like make a very, tight approximation of misclassification error and just solve that? Okay, so there's this host of developments around surrogate training losses for misclassification error. Now, what's the theoretical connection? I'm not spending a lot of time on generalization. I'm spending no time on generalization theory. But in the theoretical literature, what people are interested in is guaranteeing that if I get some small value of my fake loss, that still gives me some small value in the true loss. And the upper bound property is really helpful here. If my fake loss is an upper bound on the true loss, then I could say things like, ooh, if I get a small fake loss, then with high probability on test data, I get a small test loss. That's great, okay? And you can go further, try to argue about consistency and so on. There's a lot of things you can do there. It's impressive work. There's one sense in which it's maybe not as impressive as it sounds. For example, even regression losses like least squares or absolute error, actually they're upper bounds. They're upper bounds. Unfortunately, they go like that, right? So a lot of the sort of the hope for theoretical connection of minimizing an upper bound, that's still pretty weak, right? And you still want to argue that the upper bound isn't too far from IID. Okay. Anyway, the happy news is, if you're really committed to a hard, step threshold as a classifier, and you really want to try to approximate misclassification error, and you go down this road of surrogate margin losses, it's okay because you get everything else for free, right? So we haven't affected any of our efficient training mechanisms as long as that surrogate loss is convex. We've kept all of our same basis expansion, kernel, feature selection things. I guess I didn't show a proof, but actually, I probably should have, but it's really easy to prove that the hinge loss minimization, so if I take the hinge loss and minimize it, that's not a support vector machine, but I take a hinge loss and I minimize hinge loss plus Euclidean regularizer, that's exactly a soft margin SVM. And it just takes, it's not too hard to show that connection, okay? Of course, you normally learn about SVMs from this kind of a linear discriminant, and then you have this concept of margin and the margin through the data and so on. But it winds up, when we introduce slack variables and so on, it winds up being equivalent to just what I've shown you here. I guess I'm showing it to you this way because it makes them not look so impressive. Maybe that's a bad idea. I mean, it's a fine technology. But if you're picking margin losses, hinge, binomial deviance, they almost behave the same, and binomial deviance at least is smooth. Okay. I am testing my acuity, but I think I've got, how much time? 3 minutes. 3 minutes? Okay, that's enough time to take a big topic. Hey, I got a new plan. I'll make fewer slides tonight, and I will tomorrow teach you about multivariate extensions to linear modeling, and then go from multivariate to large structured output training, and then with light speed talk about latent variable modeling. Yeah, maybe I should just pause here, take questions, and then we actually get a break that we should have had. Yeah? Yeah, the connections, so this is all connected to maximum likelihood and map and ultimately Bayes. Yeah, I should show you, matching losses are Bregman divergences. Bregman divergences are connected to exponential family models, and if you start doing conditional likelihood training in exponential family, you wind up minimizing Bregman divergences. All of these things are connected. So I was hoping to show you probabilistic models. Maybe I can just say something quickly. All of the models that we're learning right now are point predictors, right? Input comes in, single prediction comes out, and it's a point prediction, right? What you might be interested in, though, is not just a point prediction, but a point prediction with some auxiliary measure of uncertainty in that prediction, like maybe a distribution would be, meaningful, or a point prediction in a variance, or a point prediction in some entropy, something, right? And so that extra something, some measure of uncertainty in the predictions, is what's missing from all of what I've shown you so far. And it might seem like it's a completely separate development to recover all of that, but it's actually the same thing. It's just a small extension. So you can extend all of the modeling I've shown you to exponential family to get legitimate conditional distributions. And then the point predictors are the posterior expectations, but associated with that there is a conditional distribution. I'll see if I can fit that in. Oh, maybe I misunderstood your question. I thought you were sort of asking about probability modeling.
What I mean is, what you were calling a transfer function, why can't you just logistic function and then instead of loss function is maximum likelihood?
So that sounds like a different idea. It's the same idea. So what I'm trying to explain is you wind up exactly with this, right? We could talk. Maybe I will talk about that tomorrow. Yeah. Any other question? Okay, thanks.